Hello and welcome to Dr. Jim's Structures class, where we do structures by example. Thanks for tuning in.
Man's practicing fuzzy math again.
This is part 2 of a series of videos on the analysis of pin-jointed frames. The previous video introduced pin-jointed frames and described the principles used to analyse them. If you'd like to watch that video, click the link on the screen. This video introduces the analysis of pin-jointed frames using the method of joints. So, let's get to it. The frame to be analysed has a knife edge support at A and a roller support at E. In other words, it's simply supported. There are point loads at joints B and C. The previous video explained why the method of joints only works for joints where there are only one or two unknown forces. Currently, all the joints have 3 or more unknown forces acting on them, so where to start? Inspection of the frame shows that finding the reactions will reduce the number of unknown forces at joint A and at joint E to 2. Start by drawing a free body diagram bubble that cuts the beam away from its supports. The purple lines represent the cuts, and these cuts expose the unknown reactive forces. If this makes little sense to you, click the link on the screen to find out more about cuts and free body diagrams. Dr. Jim tells me that it's one of the most important concepts in structural analysis. Next, draw a free body diagram for everything inside the bubble, remembering to include the unknown reactive forces exposed by the cuts. And note, the directions chosen for the unknown forces does not matter. The arithmetic will sort it out. We're dealing with a plane structure, and that means there is a minimum of 3 equilibrium equations available to us. These equations are commonly expressed as 1. Horizontal forces must sum to 0, 2. Vertical forces must sum to 0, and 3. Moments about any point must also sum to 0. Starting with horizontal equilibrium, we see by inspection that HA is minus 40 kilonewtons. Inspection of the free body diagram shows that taking moments about A will yield VE, the vertical reaction at E. Remember, when writing down equilibrium equations, always say what you're doing. So start by stating the sum of moments about A equals 0 and that counterclockwise moments will be taken as positive. The resulting equation shows that VE is plus 60 kilonewtons. Next, sum vertical forces to show that VA is plus 40 kilonewtons. Now replace the labels on the reactions with numerical values, noting that the arrow representing the horizontal reaction at A has been turned around to lose the negative sign. Erase the bubble and the calculations to free up space. If you want to see a more detailed video on finding reactions, then click the link on the screen. To proceed requires a sign convention for the internal forces in the structural elements. Pin-jointed frames loaded only at their joints carry only axial forces, and here is a graphical representation of the sign convention we use. Note, 1. Tensile axial forces will be regarded as positive. 2. Tensile elements are referred to as ties. 3. Compressive elements are referred to as struts. And 4. The arrows represent the forces that the members exert on the joints. Make sure you understand that. The sign convention is covered in more detail in the previous video. If you'd like to watch that video, click the link on the screen. Applying the method of joints starts with identifying a joint where there are 2 or less unknown forces. Here there are only 2 candidates, joint A and joint E. We have to choose one, so let's start at joint A. Draw a free body diagram bubble that isolates joint A. Next, draw the free body diagram showing everything inside the bubble. remembering to include the unknown member forces exposed by the cuts. The unknown member forces are always assumed to be tensile. When considering joint equilibrium, only two equations of equilibrium are meaningful: the sum of horizontal forces and the sum of vertical forces. Both unknown forces would appear in the sum of horizontal forces, so start by summing vertical forces. The method of joints invariably requires resolving inclined forces in the members into their horizontal and vertical components, and that involves either similar triangles or trigonometric functions. Unavoidable, but messy. This is example 1, so Dr. Jim has chosen a structure where each triangle on the space diagram consists of a right angle and two 45-degree angles. 45-degree angles are handy as the sine of 45 degrees equals the cosine of 45 degrees. Sines will be used throughout. We're keeping things simple. Summing vertical forces shows that FAB is minus 56.57 kilonewtons. The negative sign means the force in member AB is compressive. It's a strut. So member AB is pushing on joints A and B. Summing horizontal forces shows that FAC is plus 80 kilonewtons. The positive result means it's in tension. It's a tie. So member AC is pulling on joints A and C. Next, remove the free body diagram bubble and record the results on the free body diagram for the whole structure by drawing arrows on members AB and AC to indicate the nature of the member forces. Note, the force values are always positive. We have finished with joint A, so remove the calculations to free up screen space. Note, if doing the calculations on paper, all the working would be retained. To continue the analysis, identify another node with only one or two unknown forces. Notice that the analysis of joint A has reduced the number of unknown forces on joints B and C. Joint B now has two unknown forces acting on it, and joint C has three unknown forces acting on it. We can't solve for free forces, therefore joint B must be solved next. So draw a free body diagram bubble to isolate joint B. Next, draw the free body diagram for everything inside the bubble, remembering to include the unknown member forces exposed by the cuts. Note again, the unknown member forces are assumed to be tensile. Summing vertical forces shows that FBC is plus 56.57 kilonewtons. It's positive, so member BC is a tension member, a tie. Summing horizontal forces shows that FBD is minus 120 kilonewtons. It's negative, so member BD is in compression. That is, it's a strut. Remove the free body diagram bubble and record the results on the free body diagram. Then remove the calculations to free up screen space. Inspection of the free body shows that all remaining joints have only two unknown forces acting on them. The order in which the joints are solved does not matter, but to proceed, one must be chosen. It makes sense to work methodically from one side of the structure to the other, so joint C will be solved next. Draw a free body diagram bubble to isolate joint C, then draw the free body diagram for everything inside the bubble. The equation of vertical equilibrium will be applied first. But why not the equation of horizontal equilibrium? What do you think? Well, there's a good reason. Both unknown forces would appear in the equation of horizontal equilibrium, and a single equation with two unknown forces can't be solved. Applying the equation of vertical equilibrium shows that FCD is plus 84.85 kilonewtons. It's positive, so member CD is a tension member, a tie. Summing horizontal forces shows that FCE is plus 60 kilonewtons. Again, it's positive, so member CE is also a tie. Again, remove the free body diagram bubble, record the results, then erase the calculations to free up screen space. Are we bored yet? Joint D will be solved next. Draw a free body diagram bubble to isolate the joint, then draw the free body diagram for everything inside the bubble, remembering to include the internal member forces exposed by the cuts. Applying the equation of vertical equilibrium shows that the only unknown force, FDE, is minus 84.85 kilonewtons. It's negative, so member DE is in compression. It's a strut. Remove the free body diagram bubble, record the results, and then erase the calculations. Inspection of the free body diagram shows that all member forces have now been found. Is there anything more to be done? Technically, no. We are done. However, it's important to realise that the method of joints requires a lot of fiddly, error-prone calculations, where each new calculation depends on all the preceding calculations being correct. Comprende? Wouldn't it be nice if there was a simple check we could make? Well, fortunately there is. If joint E is in equilibrium under the action of the member forces and the reaction force, then that is a powerful check that the calculations are accurate. Let's try it. Draw a free body diagram bubble to isolate joint E. Then draw the free body diagram for everything inside the bubble. Next, some horizontal forces, and then some vertical forces. In each case, the forces sum to 0, showing that the joint is in equilibrium. And this validates all our calculations. Woohoo! Victory can be declared. You will have noticed that the screen has been tidied up at various points during the analysis to free up screen space. This is fine for an educational video like this, but when solving problems on paper, all working should be retained. Why? 2 reasons. It is important that all engineering calculations should contain enough information to allow checking. The other reason is that your working may well be worth marks. And that concludes the analysis. If you would like a free, printable, annotated set of notes for this video, then swing by Dr. Jim's website at drjimstructures.com. In the next video of this mini-series, Dr. Jim will analyse the frame using LinPro, a free, lightweight frame analysis program. To watch the LinPro analysis video, click the link on the screen. Well, thanks for watching. If you found this video useful, please give it a like and feel free to comment. Your feedback is appreciated. Bye for now. Hope to see you again soon.
Phony numbers.
If I could respond to that.
Let me just tell you what the facts are.